Hi, everyone. Thanks for coming. Sorry to interrupt. No, it's all good. It's all good. Thanks for coming to this talk. I hope you're feeling nourished after lunch. If we haven't met yet, my name is Nick DeMarco. I'm a senior computer scientist at the Software Technology Lab at Adobe. And today, I'd like to do something kind of fun. I want to reintroduce you to generic programming. Now, if you're here in this room, I suspect that you probably have some familiarity with what generic programming is. But today, I'd like to ask you to approach this with a beginner's mind. And if you do, my hope is that we can build up the intuition for this school of thought from first principles. So we're going to focus less on tricky template syntax, although it will appear in the talk, and focus more on essential ideas. So let's begin with the basic motivation, or what I think is the basic motivation of generic programming. And that is that all code is a liability. That might be like an unfamiliar phrase to you, and if you're like me, it might be a little bit unsettling considering we write code for a living. But it's true. Code is static in a dynamic world. Operating systems change, frameworks change, even languages change, and rotting code needs to be updated. That makes it a liability. So naturally, we should want to reduce our liabilities, and if we accept this, we should aspire to write less code. And if we want to write less code, we're going to have to write different code than we're used to. That might come with some trade-offs like familiarity or teachability and so on, but we can manage those trade-offs and make some principled design decisions if we do. And because generic language features can be a little bit intimidating, maybe a weird choice, I decided to start today in TypeScript. And my hope is that the more approachable syntax can help us focus on ideas rather than the finicky details. OK. So I bet at some point in your career, you have submitted code like this for review, and your benevolent reviewer suggests, make it generic. What do they mean by that? I find 9 times out of 10, they probably mean this. Instead of array of number, you should take an array of t. And their intention is to make the function more reusable, and it is. We're moving in the right direction. But it's not really clear what principles motivate this change. And my hope is if we understand the principles, we might be able to make a better design choice. This is not the only option that we have, really. This is just one point on a spectrum of generality. Now, on the left, we have the maximally constrained signature. One type is valid if we ignore things like conversions for a second. And on the right, we have the maximally generic function. That's a signature that accepts any argument, not an array of anything, but anything. And what our reviewer suggested was that we land somewhere around here, accepting any built-in array. And if we remember that our goal is to make our function more reusable so we can write less code, my question now is, can we do better than this? And to find out, we should give this code a bit of a test drive. So in TypeScript, you might be familiar that there are some array specializations that are used for performance reasons. And one of them is int32 array. The details don't really matter, but it's called an array, so we should expect that our function is able to sort it. But if you try, you'll get this error, which I think is pretty instructive. Argument of type int32 array is not assignable to a parameter of type t array because it's missing some methods, pop, push, concat, and a handful of others. Now, I think we can agree you don't need to look inside of the implementation of sort to know that we don't need pop or push or concat to implement it. We're asking too much of our argument types. In other words, we've over-constrained our function. In other words, that tells us that the ideal position is a little bit to the right on this spectrum that we have here. But then the question is, how far do we go? How far to the right do we push this thing? How generic can we make this interface? And to answer that, I thought it'd be fun if we try to see what breaks if we push it to the limit and go all the way to the right. What's going to happen? This time, we actually need to look inside the implementation of sort. And sorry, just bubble sort for the sake of demonstration. Don't ship this. But notice how we use our argument c. We read its length property and index into it with numbers. And if we try to compile this, those uses are going to cause some issues. And why is that? The compiler can't guarantee that our totally unconstrained argument will have a length and an index operator. We haven't constrained our function enough. It's too generic. All right, maybe we're making some progress. We're kind of bisecting our way to the right choice. I hope it's clear that we kind of want to make a choice somewhere around here, where any type with the required functionality is valid. But then the question is, how do we do that? I'll tell you right now that it's going to cost us more characters, but that trade-off is going to get us a signature that will help us hit this mark a little bit better. So let's start where we left off with our maximally generic function, and we'll incrementally add some constraints. So we'll start with that unconstrained argument C. And to do this in TypeScript, we say extends bracket bracket. This doesn't add any constraints on C's interface. It just requires that the argument is non-null. But that's not really important for our purposes, so we can kind of ignore it. This doesn't introduce any new syntactic constraints. So let's add some. First, we specify that our argument has to have a length property of type number, and that we can index into it with numbers as well. That's what that nifty syntax looks like there. And then to specify what that second operation returns, we have to introduce a new type in our signature. Let's call it T. All right. And then we're going to indicate that that element of type T is returned by the indexing operation. So we have one more constraint here, but it's actually pretty subtle. The constraints, at least in TypeScript, are mutable by default, but we're never actually reading C's length property. Excuse me, we're never writing it, but we're just reading it. But as written, our constraints are going to reject arrays with immutable lengths. So we can just add read-only to that property. And with that, we've expressed all of the constraints on sort that we possibly can. And now, as C++ engineers, you might be wondering if we also need to constrain T to be comparable with the less than operator. Like we're doing that right there. Don't we need to say something about that? And normally we would, but in TypeScript, all types are comparable by default. So, right, you should laugh at that. So there's no meaningful way to express only allow types with a comparison operator. So we're just going to ignore this. But in other languages, like C++, you would want to add that constraint, but we can ignore it for now. So now let's give this a try and see how we do. Now, our interface is going to work for int32 arrays, built-in arrays, and just about any other sortable thing that we could throw at it. And importantly, if we try to sort the unsortable, we're going to get a compiler error. So we're moving in a good direction here. Like I said, it costs us a few more characters, but it seems now we've hit our mark. Our sort function accepts any type with the required functionality. If we make our interface any more generic, our arguments won't have the API that we need to sort them. And if we make our API any less generic, we will leave sortable types behind. So it seems we found an optimal choice. I have a question in the back. Yeah.
Is this orthogonal to like our comparison function?
Is this orthogonal to our comparison function?
We're kind of constraining to non-decreasing order, right?
Yeah, totally. Yeah, for this simple example, we are constraining. We're just doing non-decreasing order. Good question. So our first key takeaway is to maximize reusability with minimally complete constraints. Minimal, meaning we're not overly constrained, like I said, and complete, meaning we're not overly generic. And you might notice my little foreshadowing asterisk there. Later, I'm going to introduce a principle that's sort of in tension with this, but we'll cross that bridge when we get there. So let's say we do this analysis with other algorithms in your code base, like sort subrange or nth element. And you find that each of them have the exact same constraints. And the engineer in you says, don't repeat yourself, right? Naturally, we want to lift this into some new named entity and refer to it in each of these signatures. And syntactically, that's not hard. We're just going to use an interface in TypeScript. Really, the hard part is naming this thing. Like, what do we have here exactly? Well, when you're faced with naming something, I encourage you to look outward, not inward. In my experience, good names rarely emerge from staring at the wall and thinking really, really hard. They come out of domain-specific research. Like, what do other people call this thing? And in this case, because we're talking about something like sort, a good place to look might be the standard library documentation. So that's what I did in preparation for this talk. So here I have two excerpts from the built-in array.sort method. And it says, the sort method is generic. Nice, good sign. And it only expects the target object to have a length property and integer keyed properties. Sounds like what we have here. And it also says, although strings are also array-like, blah, 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 the immutability of strings doesn't matter right now. What does matter is the use of this phrase array-like. That seems like the term that they're using to describe the interface that we have here. And the author didn't just pull this out of thin air, right? They're alluding to an interface in the TypeScript standard library, that type. That's almost exactly our interface, only our array-like elements are mutable. And so to reflect that, maybe a good name for this would be mutable array-like. And I guess good is a relative term here. Like, to be clear, I don't think array-like is a particularly good name. It doesn't tell you what it really means to be an array or what parts of an array you have to be like in order to satisfy it. And we're inheriting all of those problems by choosing mutable array-like for our name. Good naming deserves its own talk. My only point now is please lean on the existing naming conventions in your standard library when building something like this. But anyway, we're not done with this thing. We need to add documentation to explain the semantics of it. And now you might be thinking, Nick, these names, they're perfect. They're so totally unambiguous that there's no need to document the semantics. The intention is totally clear from the code. You're wasting characters. And I get it. I've heard this a lot, and I've written plenty of undocumented code myself. And to make that argument better, it seems even the TypeScript authors didn't bother to document array-like. There's no in-source documentation, and all I could find online was this, which adds exactly 0 semantic information about what array-like is. I assume this website is generated from scraping the source code. I'm not trying to pick on the TypeScript team, mostly. My point is this matters a lot. Because remember, our goal as generic programmers is to write less code. And we do that by writing components that maximize reusability. We want to have a lot of clients. So maybe 99.9% of the time, our perfect names make the semantics of mutable array-like totally unambiguous. But 0.1% of a huge number of clients is still a huge number. Guess what you get, for example, if you Google TypeScript array-like. I don't think a Google search is scientific, but I think it's really compelling that that question comes before the official documentation. That's probably a bad sign. And granted, this is really a question about how the language works, but I think it's a missed opportunity to teach users directly through the source code. 5,000 people ended up here and were confused about this thing. We can probably do better. The nice part is, the way I've been taught anyway, it's not a massive amount of work. In a lot of cases, a simple sentence fragment doc comment can get you pretty far. Just explain what the thing is. And please have some sympathy for that Stack Overflow user and document the members as well. Now that user has a hint as to what that index syntax actually is doing. Maybe that comment is all they would have needed to understand that language feature. And maybe 99.9% of the time, it was totally unambiguous that length meant length of or number of elements, but you just saved the 0.1% of users that are going to get confused and think that it refers to length in bytes. That might be worth something. Now I have a slightly difficult point to make because it has to accept some harsh truths. Obviously, we should document all of the semantics of our code. The semantics of all of our code. That's the only way that we can evaluate the correctness of it. But also, obviously, we have deadlines to hit, and that means corners are often cut. Sometimes you skip writing documentation, and that's bad. But if you skip documenting generic components, that is extra bad. And my reasoning for this is when you encounter undocumented, non-generic code, you at least have the fallback of inspecting the implementation and deriving the semantics for yourself, the sort of works as implemented contract. But with generic code, a lot of the time you don't have that option. You either have to guess or look at uses of the component and then derive its semantics from that, and you're probably going to get it wrong. So to be clear, document all of your code, but especially document all of your generic code. Don't cut that particular corner. And that brings me to key takeaway 2 of 8. Extract common constraints and document their semantics. So once you do that, what do we have? Like, what is that thing? Mutable array-like is a bundle of syntactic constraints and associated semantics. We discovered it by noticing common constraints across similar algorithms. And notice these semantics are intertwined, right? The length tells you the valid range of values for the index operation. That's important, and it's a strong hint that we might be talking about a concept. If you're not familiar, this is Alex Stepanov and James Dennert, clearly both fans of the intellectual chin support pose. And in one of the earliest texts about generic programming, they say that we call the set of axioms satisfied by a data type and a set of operations on it a concept. And axiom is just a fancy word for the semantics that we documented in our comments a second ago. And they go on to say we want a minimal set of these concepts, which match as many concrete non-generic program structures as possible. I kind of like to think of this as looking for the basis operations of computation, like a set of operations that will let us easily express virtually any algorithm. And we'll probably never have a completely satisfying set, but in pursuit of it, we can incrementally reduce our code duplication. And importantly, we don't find concepts just by lifting out the common constraints of a handful of algorithms. We discover them by doing this type of analysis on the broadest possible set of real concrete code examples that we can get our hands on. So, is mutable array-like a concept? Maybe. To increase our confidence, we'd probably want to look at a lot more algorithms than the 3 we've seen so far. And this time, we were pretty lucky that the few that we looked at had the exact same syntax. That made it particularly easy to extract their common constraints. But if we do our due diligence and look at a large number of concrete components, there will inevitably be times when we express the same abstract idea, the same concept, but with different syntax. So we're going to need a technique to lift out those commonalities too. And to best do that, I'd like to switch languages. Back in familiar territory, let's say I have the simplest possible linked list, right? I have a head pointer, there's some nodes, they have values, they have next pointers, no tricks. But now, let's say we wanted to count all of the instances of a particular value in our list. We might write an algorithm called count and do an interface something like this. And the highlighted syntax here is just saying the same thing as we saw before with t extends equality comparable, like we might have said in TypeScript. Different syntax, same idea. We're constraining our interface to only accept types of t that support equality comparable. And what that means in a little bit more detail is that for any 2 t's, we require that equality and inequality expressions are legal and meaningful. In other words, that we have the double equals and bang equals syntax, and that syntax has the expected semantics, not just any semantics. And don't worry about how we implement this thing yet, we'll get there. But then we implement our count algorithm like this. Again, it shouldn't be too surprising. We just iterate through the linked list, and as we find the value we're looking for, we increment a count, we return the count. Hold that in your head. We'll be right back. This is a different class. It's called user input. And user input requires its template type t to be input streamable. I made that up. But in C++, the most idiomatic way to express serializable from a byte stream, which is what we're going to need user input to do, is to support a double chevron operator with a standard iStream. So when we say that something is input streamable, we're just saying that this syntax is legal and has the expected semantics, right? We build a t out of a stream of bytes. And then we give it a pretty simple interface. It just has one read API. It'll return an empty optional if there's an error or the stream is closed. No surprises. And just like before, we'd like to count the number of times a particular instance of a type t appears in our sequence. So we might write a count algorithm like this. And you probably see where I'm going with this. If you recall our implementation of linked lists count, this has a very similar structure, right? This is expressing the same idea, but with slightly different syntax. And it's not going to be as simple as what we did with mutable array-like to extract this out into a new named entity. So our goal now is to get these common constraints out and define a new abstraction to do it. And to do that, we use a technique called lifting. So at the bottom here, we have a little bit of pseudocode that expresses like the general idea that we're trying to model here. And to do this in C++, we're going to use the concept keyword. So what's a concept, at least in the language? You can think of a concept as just a compile time Boolean. It really is like fundamentally just a const expr Boolean that evaluates the properties of some template types, in this case, I. And a requires expression is going to declare operations on that particular type, I, that must be, again, legal and meaningful for I to satisfy the concept. And now to make this abstraction, one point that I'm going to drive home in this talk a couple of times is that we don't need to design really anything. We just need to codify the semantics we're already seeing from the concrete code examples that we're analyzing. So first, we just need a way to get the position after I. And instead of the pseudocode get next, how about we use like a pre-increment operator? That operator is either going to return the next position or some invalid value that represents the end, some sentinel value. And that'll be our abstraction over null pointer and null opt and things like it. And next, we can use the dereference operator to get the value at the current position. And the type of the value that's returned here is not I, it's going to be something else. So just like we saw with mutable array, like we need to introduce another type here and then put it in our template declaration. And then finally, we need a way to compare these things. So because we say in our documentation here, we need to check if we have a valid position or not before we can dereference it. And we already know the concept for this. I showed you a second ago. It's called equality comparable. And we can build on that concept like this, right? And here we've got another hint that concepts are really just fancy context for bools, right? We're using the double ampersand, just some Boolean logic to say that our concept requires equality comparable and the subsequent operations that we describe. So now that we have the semantics for what this thing can do, we can try to give it a name. You probably see where I'm going with this. Someone shouted out. This is a position. This is an iterator. That's right. Cool. This is an iterator, or our approximation of one. But we're not quite done here. At the moment, on the right-hand side of these arrow expressions, we have some types. Reference to I, reference to T, a Boolean. But C++20 doesn't allow that. It requires that we put concepts there, not types. So we're going to use a helper concept called same as. And if that's a little disappointing to you, trust your instincts. But we'll take what we can get, I suppose. Now that we have a concept, though, we just need a small amount of work to map our existing code into this abstraction. We'll look at our linked list, and we'll define an internal struct list iterator that'll translate the list-specific logic into our iterator abstraction. First, we need to be able to have our list tell us where it begins and ends. So we're going to add those functions there. And intuitively, we're just going to use the head pointer to indicate the beginning and a null pointer, that's sentinel representing the end, to indicate where the end of our list is. And the iterator itself doesn't require much at all. It's just going to hold a pointer to a node, which crucially is exactly what our original concrete algorithm had to do. We don't want our iterator abstraction to be more costly than doing things non-generically. And then we just need to add increment, dereference, and equality. And we can do that in about 3 lines here. If you're not familiar, I'm just using a defaulted operator equals. As of C++20, that is going to synthesize a reasonable not equals operator. So you'd save yourself some characters. And then to implement increment and dereference, we're just going to do this. And really, the only gotcha here is that you need to return a reference to the iterator when you increment it. But other than that, this should be pretty intuitive. And then finally, if we want to specify that our begin and end methods return a concept, we can constrain our auto return type with a concept like this. Right? That'll give clients a bit more context and ensure that whatever we return from begin or end actually satisfies the concept that we care about. And now, in the interest of time, we're going to skip implementing user input iterator because that's basically the same as an iStream iterator from the standard. But if you're curious how that works, I thought it was interesting. You can follow that link there. But now let's try to write our count algorithm in terms of this new abstraction. So just like our use of equality comparable, this declaration here is constraining our algorithm to only work when our second and third arguments are iterators over t. So now we have everything we need to write a single implementation of count that works for both of these things. Both of these iterable things, anyway. But what's an iterable thing? You know, the engineer in me is saying, don't repeat yourself. And the generic programmer in me is seeing that these have identical semantics. This smells like a concept. And fortunately, this time, our job really couldn't be easier. We have some pretty clear semantic and syntactic repetition. Right? We just need a name for this thing. And this, I'm borrowing from the standard here, is usually called a range. And this is almost identical to the one shipping in the standard library, more or less. There's just one little difference. If we want our concept to have the widest possible use, it makes sense that we would want built-in arrays to also be ranges, at least sized ones, right? But it won't because arrays don't have methods, right? But that's an easy fix. You might know the old adage, all problems in computer science can be easily solved with one layer of abstraction. We can make begin and end free functions like this, and then treat them like an overload set. So for objects that do have a begin, we'll call begin on that object. And for arrays that do not, we'll just return a pointer to that first element. And just like that, our concept supports built-in arrays. So let's actually use this thing. iterator, and range. We can define a count interface in terms of these two concepts that we've discovered. Any range of equality comparable t's are valid arguments, or is a valid argument to this function. And then we can implement it like this. Very similar structure to before, only now we've abstracted away all of the particular implementation details of our two data structures. And maybe I just need to get out more, but I actually think that's pretty beautiful. Now our algorithm directly expresses the intent of count. We're not burdened with the implementation details of either particular data structure, and assuming that a type supports the iterator concept, this is going to work with virtually any sequence. And my point in kind of laboriously going through this is to show you that we didn't do much design, really. Like, at most, we picked the particular syntax for increment, dereference, and maybe equals, but we didn't design complicated new semantics to discover what iterator was. We let the concrete implementations of count reveal the semantics that already made sense, that already worked for a real-world use case. And that leads me to my third point. I'll get you in one second. Concepts are not designed, they're discovered by analyzing algorithms. Question in the back.
So I would think like the iterator concept there, especially with the streaming thing, you're over-constraining it to be an L-value reference.
Absolutely.
And like for like when you're reading stuff, you're forcing it to hold on to it, whereas if you could just return it directly, it would be like it's, you know, like if you were designing from scratch, you might have just removed that and made it either L value or R value and not constrained it like that.
Totally. I'm going to invite you to put your beginner glasses back on, and we don't know what L values and R values are right now. We're just going to forget that, but excellent point. Yeah, if we were designing this from scratch, we would have to take that into consideration. So concepts are not designed, they are discovered. And fortunately, you're not alone if you go on this journey. There is a huge body of work already done to identify important foundational concepts. And maybe the most famous one of all is called regular. And in the same article that I referenced earlier, Stepanov and Dennert give us a definition. They say, if we hope to reuse code which uses the standard C++ operators, we must extend the syntax and semantics of the standard operators to user-defined types. And a regular type, then, matches the semantics of built-ins, making our user-defined types behave like built-in types as well. So a regular type matches the semantics of a Boolean or an integer or a character or a pointer. In other words, it has the semantics of a value. This might feel like a bit of review for the folks that attended Tony's talk yesterday. But when discovering regular, the authors identified this set of basis operations that all of the built-in types supported. And they put forward the idea that types that emulate these semantics would be more easily used with standard generic algorithms. And then there's kind of a quirky case here. Over time, like the generic programming community sort of discovered that ordering doesn't really belong here. It's kind of orthogonal to the other lifetimey notions that the other semantics refer to here. So even though the built-ins support ordering, like you can order bool, it's sort of orthogonal to these other things. So we're just going to put that into a different concept. The rest of these, however, form the backbone of the concepts library that we got in C++20. The standard library folks spent a lot of time, as I understand it, analyzing loads of algorithms to formalize this taxonomy of concepts. For example, to be regular, you have to be something called semi-regular and equality comparable. To be semi-regular, you have to be copyable, and so on. And these groupings, if you just glance at them, might look a little bit arbitrary, right? You might be wondering how they decided to arrange this taxonomy. There's definitely not one obvious way that we could do this, right? Well, the way they did it is when analyzing algorithms, they paid close attention to how the semantics of each operation were intertwined. And in this talk, we've already seen some examples of this. Yeah?
Yeah, so I think the regular types were defined pre-C++11, like what after 11, like the move semantic and everything, what changed what would be the regular type, or would it just like maintain the same as the table right there?
After C++11 with move semantics, you would need to consider move operations to be regular. But in 1998, they didn't have that. And we're going to start from there.
What will be the other difference? Is it just the move constructor, or?
Move constructor and move assignment, I think, yeah. So in this talk, we've already seen some examples of intertwined semantics. This is a new idea I want to introduce here. So In the mutable array-like example, we use the length property to properly determine, or to determine the valid arguments to the index operation, right? Like we use the size to determine like, hey, is this a valid argument to index, or am I gonna go off the end? And with our iterator, we use equality comparisons to determine if it's valid to dereference at a current position. So equality and dereference have this relationship. And with our range, maybe this is the best example of all, clearly begin and end are intertwined. You can't have one without the other. Don't bring up infinite ranges. My point is a good concept should be an encapsulation of operations that depend on and relate to each other. That's crucial. And it's a good sign that you found a meaningful abstract entity. So for example, think how you would define the semantics of copy. What does copy mean? To define it meaningfully, you would probably have to say something like a copy of A is equal to A. What does copy even mean if you can't talk about equality? You might try to skirt around it and say something like, for all functions f of A equals f of B, but you're still talking about equality. You've kind of kicked the can down the road. So my point is these two ideas, equality and copy, are closely intertwined. No matter how you slice it, and this is what I just said, the f of A of f of B, no matter how you slice it, you're talking about equality when you talk about copy. Another example that I like here is independence of assignment. Here we assign C to A and B, and then perform some operation that always mutates A. And in C++, we expect this assertion to always hold. Not only that A and B are now different, but that the untouched B and C remain equal. And I bet you can imagine a language in which that assert might be false, right? It's probably a reference semantic language where mutating A would mutate all of the references to A as well. But in C++, that's not how assignment of built-in operators works. So to be regular, we expect distinct objects to be distinct. My point is these semantics are interconnected, right? Construction implies destruction. Copy implies equality. Equality implies inequality. These ideas build on one another. But of course, there are cases where you can be constructible but not comparable. And so the standards folks broke up this taxonomy into groupings that correspond with real-world use cases. And now I added this today. I don't really want to get into the weeds, but there is one interesting example with semi-regular that was driving me nuts. By definition, that thing is copyable, but not equality comparable. But I just said that copy implies equality. What gives? Well, if you're semi-regular, you can't ask if two objects are equal, but the semantics of equality still matter. Because if you're semi-regular, you're copyable, and if you're copyable, you're copy constructible. And if you're copy constructible, you still have semantic requirements. After a copy construction, you must equal V. You can't check, but you have to be. I think that's very interesting. So key takeaway 4 of 8. Define concepts with intertwined semantics. All right. Yeah, hey.
This is a point that's always been weird to me when I go try to like figure out what regular means. This is the best exposition I've seen of it. Thank you.
You're welcome.
You get lost in all of these. Oh, there are these certain syntactic constraints, but also here are a bunch of semantic constraints using a terrible amount of standard ease.
Yeah.
Do you have any thoughts about the fact that concepts are a feature that the language lets you check syntactic things, but we're using them also for semantic things that cannot be checked? It's a very open-ended question.
No, I like the question. No.
But it's okay if you don't have it.
That's what we're doing here, I think, philosophical. There will always be semantics that we can't check. Yeah. Right? There will always be, you'll never be able to write, is this iterator reachable from this first iterator? Yeah. You can't write that function. Yeah. Don't try. Yeah. Well, actually try, you might learn something. But there will always be those cases. So I don't think we should throw the baby out with the bathwater and say, because we can't model all of our semantics with syntax, we shouldn't model any semantics with syntax. I think semi-regular is a particularly strange example that more or less falls out of the fact that there are these kind of odd cases where you can't compare objects. The best example is lambdas. Like you should want to be able to store lambdas in some sort of container. And so you probably want it to be copyable, but they don't support equality. Yeah, so what do? Right? You say, well, it's a semi-regular thing. It's almost regular, but you need equality to be regular.
Sometimes equality is not computable or practically.
Exactly. With functions in particular, equality is not necessarily computable.
It's there, but you cannot access it. It's like
Exactly, exactly. And then you have more like the observable properties of equality, right? If I call these two lambda expressions that are equal, I expect equal values out of it, even if I couldn't have checked that in the first place. I don't know if that answers or even addresses your open-ended question.
I think maybe you answered the question in the talk already. Like, I didn't realize that concept was a general concept that had come from an academic paper rather than just being a syntactic feature.
It's very, very common. I think the standard made the right choice calling that language feature concept, but virtually every talk that addresses this has to start by saying there is the idea, capital C concept, and then there's the monospace little concept.
Thank you.
You're welcome. You're welcome. Yes?
Yeah, I think we must not forget the definition of equality from CppNow, in which he says that if you apply the same regular function to both sides of the equality, you also get an equality. Because that function can bring you to, for example, the output can be ints, where you know what equality is supposedly. The same way built-ins behave like regular and all that, you can bring in two types where you know exactly what equality means, and you know that all the possible functions should preserve the equality.
Yes.
Now, that's interesting because it also makes the definition of regular function circular with regular types. So it's kind of, you know.
Yeah. When you're dealing with philosophy, and I think a lot of this is that you enter into these circular ideas that like become almost axiomatic, that you have to build your thoughts on top of these things you just kind of take for granted. I do want to leave regular functions alone for right now. I think just to sum up that point, you can observe equality, the properties of equality, without being able to actually check it. Right? I can call the same equal function with the same arguments, and I can observe that they produce equal outputs, but I could never have checked in the first place that those functions were equal, because that's not supported or computable. Anyway, let's move on in the interest of time. So, what is this? Define concepts with intertwined semantics. All right, let's give our iterator concept a bit of a test drive here. For the sake of example, I'm going to implement the simplest possible class that conforms to this concept, a counter. All we're going to do is wrap a size t, right? And then I'm going to expose the iterator interface for it, just wrapping a size t, no tricks. And we can check at compile time if our counter is, in fact, an iterator. And it is, right? Concepts are just const expr booleans. You can use them anywhere you would expect to see a const expr boolean. So I can static assert iterator. And what really, in English, the way you would read that is I am static asserting that counter is an iterator of size t. You kind of have to jump around there. But we can check at compile time if it satisfies the concept. But now let's try to use our counter in a standard algorithm, like advance. And I'm going to use the ranges version because as of C++23, only the algorithms in the ranges namespace are constrained by concepts, I think. Someone check me on that if I'm wrong. But will this work? Any guesses? Yeah, I would never answer in this context either.
I'm going to go with no because there's a copy somewhere.
Good guess. It's way more boring than that. We don't support a difference type. So our iterator requires, the standard iterator concept says if you want to be an iterator, you must declare what is the type of the thing that we get if I subtract one of you from another of you, no matter what. For input or output iterator, you need to do that. So let's just add a difference type. That's sort of beside the point that I'm trying to make right now. Now, will this work?
Does it use the difference?
No, it won't work.
No, not advanced. Good guess.
Is it because of the category?
Good guess too. No. It's simpler than that. We don't have a post increment operator because post increment is not supported by our counter. And this, sit with this for a second. I'm going to tell you right now that advanced doesn't use post increment. It won't. It shouldn't, right? That would be inefficient. All it needs is pre increment. They just use pre-increment, which we provide. And in fact, counter provides all of the APIs that advance uses. So what gives? Didn't the standard see the first part of my talk 20 minutes ago when we said that we were trying to make maximally reusable functions, right? We want to constrain algorithms so any type with the required functionality is valid. Isn't the standard over-constraining advance? And it might help if we look at the concepts, or at least the documentation for the concepts. Input or output iterator requires a dereference operator combined with this weakly incrementable concept. Ignore the weakly part. It's not important for our purposes. And weakly incrementable requires both a pre-increment and a post-increment, no matter what. This is the simplest incrementable concept in the standard. You can't get less incrementable than that, I think. Even if there are plenty of algorithms, including advanced, that do not use post-increment, if you want to be incrementable, you have to support both. And that's because concepts, capital C concepts, are not just bundles of syntax with operations that have arbitrary semantics. The concept as a whole models an abstract entity. And this might be the most go-to example when people are trying to make this point, modeling numbers. There are definitely algorithms out there that just use addition or just use subtraction. And if we constrained our algorithm to their absolute minimal requirements in a sort of rote mechanical way, right, we might want the concepts that you see now. But the problem is, separated like this, these syntactical constraints have little to no meaning. What entity, what thing in real life can be subtracted but not added, multiplied but not divided? And it's precisely the relationship between these operations that give the whole thing meaning, number, right? To separate them like this is to make them meaningless. So instead, we want this totally not production concept, right? We bundle these things together into a single numeric concept, right? But you can imagine the compiler errors that I get if we deploy this, right? I try to sum a bunch of things that only provide an addition operator, and I can't because I don't support division. That might be frustrating if you don't understand the motivation that comes behind it. So as a discipline, generic programming has made a conscious choice here, a trade-off. We are not interested in making maximally reusable functions at the expense of semantic consistency. We are not interested in doing that. Semantic consistency when modeling concepts is way more important than eking out every possible iota of reusability from our functions. It's more philosophical than that. Here, the standard library is telling me I could compute this, but I won't. Because even though you have an increment operator, the only one that I use, you aren't semantically an iterator. An entity without pre-increment, an entity with pre-increment but not post-increment is like an entity with addition but not subtraction. It doesn't make sense, and we insist that you fix it. I think that's pretty important. Yeah?
So it seems that concepts want you to constrain the input, but also don't want to constrain how you implement it, even if it's inefficient. You might get an implementation that is inefficient and is post-increment. Right. It should be bad. So it's kind of both ways in some sense.
Yeah. So here the standard is saying implement post-increment, and then it's the algorithm's responsibility not to call it if it doesn't have to. Right? Does that make sense? Yeah. But good point. OK. So it seems this point on the spectrum is actually too generic. We went too far, right? We don't want to allow any type with the required functionality into our algorithms. Rather, we want any type satisfying the required concepts to be valid arguments. And it's a small difference, but it is important. So takeaway 5 of 8, concepts should model abstract entities, even if that means technically over-constraining your algorithms. OK. So we just saw a pretty big success story for concepts, I think. Our type didn't provide operations that it needed to be semantically consistent, and we got a compiler error. Nice, good. In this case, the concept-constrained algorithm was right, and this use of advanced should fail to compile. You have a question?
I think, not equals, right? Similarly, if you didn't have not equals, it would fail, saying you didn't do equality. But it synthesized it for you off equals default because of the concept.
Yeah.
Wouldn't it be better for the compiler to actually be filling out these concepts instead of forcing you to do it, so that when the dead code thing deletes one of your methods, it doesn't break your build somewhere else for unrelated reasons?
Totally. I'm hearing, why doesn't the standard also synthesize post-increment?
Or any other thing they decide is tightly enough that it should be a single concept.
I don't know the details on that. My guess is either it is not efficient in the general case to do so, and they don't want to generate something that isn't exactly right and exactly efficient, or no one's proposed it yet. You might want to propose it.
Let's add more stuff to C++.
Let's add stuff to C++ that synthesizes code for you so you don't have to write a bunch of stuff. I genuinely support that.
For the obvious cases, yes.
For the obvious cases, yeah, where there's no argument about it. All right, so like I was saying, this is a case where concepts saved us. The algorithm was right. Oh, yeah, sorry.
One of the mean, it kind of like went halfway with the post increment is like the ints return by value, right? And they left off the return type on the concept for the post increment. For the incrementable, right? They like whereas
oh yeah, weekly
to return the return return something. Like you could have a void post increment, which seems kind of weird anyway.
Yeah, good point. I hadn't thought of that. Yeah, you could add that stub that does nothing, or just does pre-increment and then returns nothing. And I guess you could synthesize that. Hadn't thought of that. It's a good point.
So you can implement the post increment that is efficient.
Yeah.
You need to return a copy.
Yeah. I don't know. I have to think about that more after the talk, but it's a good point. Okay. So like I was saying, this is a case where the concept saved us. It was a good thing. Stopped us from doing something that was semantically inconsistent. But what if the algorithm is wrong? Take a moment and see if you can find the bug. This time, don't shout it out if you find it. I don't know. It looks pretty good. Yeah. I heard one found it. Well, maybe I just messed up my slides because I tested it and it works fine. So we can ship it, right? Like it found the 2, so it's correct. But then we ship it, and then someone does that, and they get that. So what happened?
We should have used an operator not equal instead of less than.
That's exactly right. That's the cure. What's the disease?
We went beyond our constraints. Like we asked stuff beyond our constraints.
Exactly right. Exactly right. We did things that our input iterator concept does not support. We constrained our algorithm by input iterator, which is correct, by the way. If you want to write a good find, you should do that. But then we used an operation that iterator doesn't support, like you said, comparisons. But like, what is this? I thought we had a deal, generic programming. Like, remember in TypeScript a minute ago when we tried to compile a function that didn't have these, we had a type that didn't support these operations and we got a compiler error? That was pretty cool. Wouldn't that be great if we could do that in C++? It would be really great. But this is called checked generics. And the concepts we got in C++20 don't support it. If you've ever heard the phrase concepts light, this is why it's light. This is the part that they skipped. There's a good reason for it, but we'll get into it. Yes?
Maybe you will talk about this.
Yeah.
Are concepts extensible to check generics?
I will absolutely get into that,
Cool.
And it's bad news.
Oh,
So the main reason it's called concept light is this. I don't know much of the history. I'm going to level with you. I've heard chatter about it, but this was sort of before my time. My understanding is getting checked generics was considered too difficult at the time to land. So they're like, let's roll it back a little bit to something more of like an MVP, and we landed this. But what does this mean for us as generic programmers in 2024? At a minimum, this should give you some pause when defining algorithms that are constrained by concepts. It is very easy to introduce these so-called stealthy requirements. Demi Racardon from the Hilo project introduced me to that term. I think it's pretty cool. I like that. The requirement for a comparison operator here is really sneaky. It is very easy to get past code review, let alone the compiler, right? Unless you know your concepts really, really well. The actual solution to this would be a language feature, like we saw in TypeScript a second ago. But unfortunately, there is decent evidence that this feature is unimplementable in C++. So what do we do? Well, one proposed solution that you might have heard of, I don't hear a lot of people talking about this, is archetypes. An archetype is a concrete class implementation. It's not a template, it's a real class that attempts to support the absolute minimum required for a particular concept, like input iterator. Then after each algorithm that we write that is constrained by a concept, we put one of these test functions that calls our function with one of these archetypes, with a class that implements the bare minimum required to satisfy input iterator. And there's 2 big problems with that. 1, that's really annoying. And 2, archetypes are notoriously difficult to write. This comes from Boost's concept check library. I think input iterator is a relatively straightforward concept, and this is about as complicated as it gets. I can't imagine what it would require to implement the bare minimum for something like a range in C++20. That would be a lot of work. This kind of works, right? But it's pretty discouraging to take on the burden of writing one of these for every concept that we discover. Yeah.
Can I just ask, what's so bad about this? It seems to be about what's in the concept, and it's mechanically.
Are you sure you didn't miss one?
Sure, but I almost feel, I'm going to claim something here with no evidence whatsoever, but I almost feel that you could mechanically generate this from the concept. Certainly with a human brain, it seems like you can do it.
Oh yeah, it's possible. I'm not here to say that archetypes are impossible. Maybe I made that unclear.
It doesn't seem like there's any cleverness. It's all syntactic, is what I'm saying. Like, it doesn't actually.
Yes. I'm going to link to a blog post later that shows how difficult it can be to get these exactly right. Because I think in C++, it's very often that we think of designing types as adding something to like the basic struct. Logic, taking things away is hard to do exactly right. To take away the ability of like some return type to be convertible to some other value is hard to express correctly, and even harder to like realize that you have to do from a concept definition.
Okay.
I don't think it's computable just from a tool, because that would be isomorphic with building check generics.
Yeah.
But maybe, like, I don't know. Let's talk afterwards. Maybe you can figure it out.
Is
yeah.
Return true there, it's bug or it's on purpose?
Which part?
When you return equal or not equal, true.
Doesn't have to be semantically valid. It just has to support the operations. Yeah, I think that's the, this is the archetype saying, I didn't write this class to be clear, but that's the archetype saying it doesn't matter what it's doing, it just has to support those operations, right? It's basically, this is only being used as a compile time check that our find operation doesn't do more than it's allowed to. So it doesn't matter what these types return, or functions return, excuse me. Other thoughts, archetypes, questions? Yeah, there it is.
Or even the simple archetype, right? Like
Yeah.
you should have void on the operator plus because it doesn't, right?
Oh, yeah.
It's a good example because you should also have self, because that's another possible implementation. And it's possible that some code would fail with self but not void.
But not from the user using
Mm.
Like, it'd be
It
more
depends
likely.
on, I mean, you could have a static assert that the result is void. I know that's like a silly.
Right.
Yeah.
Also, this definition of the archetype will make it so that I can do dot operator equal and not have a friend equals method that is found by ADL.
Yup.
Okay, I see why this is hard.
Yes, the beauty of group discussion.
Exactly,
Yes.
It's not a single archetype. You can have a family of archetypes
Yep.
that are equally minimal in some different measures.
Yeah, it would be a lot of work. Let's put it that way. Like, it would be a lot of work for the standard to support this. I think it would be a lot of work for you as a concept discoverer to do this for every concept that you find along the way. It would be burdensome. I would like not to do it. The language should probably do it. But this is an open question, and I want to talk about this. For the rest of the conference, if you want to get my attention, just like chat me up about archetypes, because I think this is a problem with concepts that needs to be addressed. I'm not satisfied with the answer. It's unimplementable, so whatever. Like, you can never have it. That's not good enough. For folks that want to dig in more here, I have a couple of resources. The first one is the Boost Concept Check Library. Fun fact, I found this and then saw at the bottom my colleague Dave Abrahams was a co-author on it. I had no idea. I don't think this has been touched since concepts landed, and then probably several years prior to that. But they do have a lot of good documentation about archetypes, the motivation for it, some good reading, but maybe don't use the library until we verify that it works with C++20 concepts. And then I have a great blog post by Andrei Cheminsky. I hope I'm getting that close, on archetypes. Read that blog post if you're curious about why it's hard. It's, as a matter of fact, Andrei wrote a blog post saying, okay, I've defined this archetype, and then had to write a follow-up blog post saying, nope, sorry, got it wrong. I actually need to do this. It really demonstrates why it's so difficult. And then, as I said, there is some solid evidence that check generics are going to be impossible to implement for C++. Sean Baxter, here in this link, is waving the white flag on implementing it in Circle. He tried, as I understand it, for months, and wrote a lot of very thoughtful posts on GitHub Gist and Reddit and whatnot, and basically came down to the conclusion that the C++ OX generic spec was in some way erroneous, that it needed to be refined in some way. And I think what's his quote? I'm skeptical that we should expect early check generics to land in a C++ compiler, given their inflexibility. I assume he means that the generics are inflexible and not the compilers. But either way, it's not going to land. Yeah.
And so in terms of that, like, so these check generics and the attempts to try to make them happen are why the X is 2 digits, right? Like, it's C++11 instead of C++09, right?
The X, that's why,
because, like,
it took a while.
Like, there was a massive amount of work, I think like 2 or 3 different directions for trying to do this.
Yeah.
And then at the end, like, they had to pull everything out to get C++11 out the door.
Yeah, I'm sympathetic.
I a lot of people, and they were like,
yeah,
you know,
yeah, I'm sure it hurt. It continues to hurt. I can only imagine how the authors felt at the time. Okay,
well, that's
please.
If you don't bother about the semantic archetype here, why implement anything at all? It's just put semicolon at the end.
If I don't care about, well, because a Boolean function still has to return true to compile, so it's a return a value.
You can keep it unimplemented, and static assert will probably
just declare it and don't define it.
Yeah, exactly.
Well.
Ooh. I don't know. I'd have to play with it to know for sure. Yeah.
Maybe there is a reason.
You do have to instantiate it, right? The compiler needs to see the type instantiated in the test function.
Yeah.
But,
so
yeah.
If you did that, unless you're really careful, remember this was in Boost Concept Tech, which is C++03 as well.
Yeah.
So if you didn't implement it, it probably wouldn't link.
Cool. Appreciate that. I didn't know that. All right, I'm getting a time check here, and I got a ways to go. So anyway, be on the lookout for stealthy requirements. As you start defining concepts in your code base, just focus on this during code reviews. Really double check, triple check, because it's an annoying bug to run into when it happens. But for now, I can't advise using archetypes. I think it's just too complicated to advise in the general case. So just check in code reviews. Be careful for the time being, anyway. Okay, key takeaway 6 of 8. Just be careful. Okay, so I gave this talk to a colleague of mine a few months ago, and they said something that has haunted me and I guess made it into the talk. Making maximally reusable functions isn't what's needed to ship product. I'm hearing some chuckles of affirmation, and I sympathize with this. Product engineers on the front lines generally aren't interested in defining mathematically rigorous abstractions, nor should they be. Right? Their job is to devise concrete solutions to directly solve concrete problems, not to prematurely generalize every solution before it hits the market. That's not a good use of their time.
Double's not even regular. The philosophers skip these steps too.
Right. Double is not, yes, yeah. Yeah. As far back as 2002, Alex Stepanov was painting a picture of the future in which these two tasks, building systems and building generic components, were clearly separated. These are different tasks, right? Building software to solve a problem in the market uses completely different skills and techniques than what I've outlined here today. So what does that mean? First, we should not judge a fish by its ability to climb a tree. And I mean, we should not criticize state-of-the-art product code for being inadequately general. That's not what it's meant to be. And second, we should recognize that generalizing, lifting out abstractions, is a practice that only makes sense to do on existing, concrete, stable software. And I suppose my colleague was expressing something that I've heard a lot of developers express, that there's this hard boundary between product code and library code. And they said generic programming is just for the library authors, right? Those of us shipping products don't have time to generalize our code. But of course, we know that there isn't a hard boundary between product code and library code. It's more of a spectrum, right? And there's a lot of code between your UI and the standard library. Where do we draw the line? Where exactly does generic appropriate library code begin and bleeding edge product code end? And I think, I'm only speculating here, but because of this ambiguity, a lot of the code sitting on top of the standard library is never considered for generalization. And because all code is a liability, that means a good chunk of our code bases are rotting, and we're not even addressing it. Poorly specified abstractions are chipping away at our productivity, introducing safety and security vulnerabilities, and making large-scale change virtually impossible. We can't afford to only apply the lessons of generic programming to the standard library and Boost. We need to mitigate the liabilities in our entire stack. But again, where do we start? And I think the problem is that the answer to that question is not where do we draw the line, but when. Generalization only makes sense if we're analyzing concrete code that solves real problems. And if we don't do that, we are prematurely generalizing, and we're likely to create more messes than we clean up. So my call to action is to either find or form a team, a small team of generic programmers tasked with specifying, hardening, and generalizing the most stable code in your organization. Give them the bandwidth to work slowly and thoughtfully to incrementally replace redundant product code with rigorously defined general libraries. And if your organization ships more than one product, this goes double for you. There's going to be a lot of duplicated effort that you can generalize. And as Alex suggested, this doesn't need to be a huge part of your budget. But if you make no investment, your code bases will rot and you'll spend more time managing symptoms than addressing the root cause. And then, if you do that, product engineers should be empowered to use exactly as much generic code as is needed to solve whatever problem is, whatever the task at hand happens to be. And yes, we should all aspire to write code as if it were a library. But that is a statement about quality, not generalization. Product engineers, please, all I ask is that you document the semantics of your code so perhaps decades from now, the team responsible for turning your ingenuity into a reliable library has a good day. But other than that, use the features you want. All right, key takeaway 7 of 8, generalize your stable code before it rots. This is the first time that I've given this talk in a 90-minute format. So originally there were 7 takeaways, now there's 8. These are basically bonus slides at this point. But in preparing this talk, I was trying to get a grip on this notion of stable. Like, that's kind of squishy, and I would rather formalize that if I'm going to advocate that you behave based on the definition of that word. And so I asked around, and my new colleague, Titus Winters, pointed me to Leemann's laws of software evolution. Brace yourself. Here's Manny Leemann. And he's and this is one of the earlier papers that he wrote about software evolution. And he seems like he'd be a pretty fun guy to hang out with. And not just from the photo. I say that because in the introduction, he says this: the classifications of software in this paper are based on a recognition of the fact that at the very least, any program is a model of a model within a theory of a model of an abstraction of some portion of the world or some universe of discourse. I have spent many minutes looking at that quote. Any guesses what it means?
All code isn't right. It's just a simplification.
Or it's a model. Yeah, exactly. All we're doing is approximating the real world and modeling problems to try to solve them. So, in his paper, Leemann identified 3 categories of software, distinguished by the nature of the problem that they were trying to solve. I think he was a fan of chess because he uses chess a lot in his examples. And the simplest type of program that he introduces, called an S program, solves a completely specified program, like the 8 queens puzzle. You might be familiar with this. It's just a quirky little chess puzzle. Can you arrange 8 queens on a chessboard so none of them are attacking each other? That's it. It's a simple problem. It's been solved for years. But my point is, it's very well specified. There's a yes or no answer. Can you produce that? Yeah, that's the 8 queens puzzle. And we can evaluate an S program by their ability to solve a totally specified problem. Maybe we give them bonus points for doing so performantly, right? But their correctness evaluation is totally binary. Do they or do they not solve the problem they were tasked with? It's the simplest type of program. And then P programs are a little bit more complicated. They solve a problem with such a broad domain, kind of like playing chess, not just that chess puzzle, but playing chess in general, that they have to model the problem and then approximate the solution. This is the essence of Leemann's quote from a second ago. A chess solver, at least for now, as far as I'm aware, can't generally enumerate every possible move and branching consequent moves before deciding what to play. So those programs have to use some heuristics. They have to prune the decision tree to find a good answer in a reasonable amount of time. And that's a model. That's an approximation of the problem. That's not actually solving a problem the same way that the 8 queens puzzle is solving a problem. And then, of course, evaluating P programs is harder because their quality is subjective. It's not binary, right? And while iteration on a P program might improve the model and therefore the quality of the output that we get from it, the spec doesn't really change. It stays at play chess well. The spec is pretty static. And then finally, E programs are what you're probably used to in your day-to-day life. E programs are embedded in their environment. This is a quirky idea, another example of why he would have been fun to hang out with. And therefore, the programs themselves are included in the program's model of the world. So does that like make sense? Like Leemann saw a difference between a chess program, which has a clearly defined universe, right? Just the universe of chess. And these E programs, where the programs themselves exist in the universe they're trying to model. Like imagine a delivery truck scheduler. The program, if it's doing things right, would have to consider its own latency when modeling the scheduling program. It's in the model, kind of recursively. So any modern software tool, I think, that isn't solving a very narrow problem is probably an E program. So why does any of this matter? Like fun taxonomy, cool quote, but like why do we care? Then Leman identified these, well, he had 8, I'm showing you 4 laws of software evolution. And a lot of these to me are just, I take as given. E-programs must be continually adapted or they become progressively less satisfactory. Every product manager I've ever spoken to has confirmed that. Increasing complexity. As e-programs evolve, their complexity increases unless work is done to maintain or reduce it. Would anyone like to argue against that law? That's what I thought. Declining quality. The quality of an e-program will appear to be declining unless it is rigorously maintained. So these are nice, like these are decent adages. And it makes sense, right? A program that's solving a problem like edit a photo, like for Photoshop, just edit a photo, is going to have a different complexity growth curve than, say, a program just to play chess. With a chess player, there's a bounded domain, so it's unlikely you're going to end up building, like bundling in random DLLs to support odd corner case features for a small subset of your user base that you can never take out for reasons. Like e-programs are not just more complex, they grow it with greater speed in complexity. Yes?
I want to add some color. I think it's fun to label these with the years in which they were stated. The first 3 were from 1974, and the declining quality is from 1996.
Wow.
I think that tells you something about what we learned about software over time as the software world changed in those 20 years.
Wow. Did you know Leman before this, or are you looking this up right now?
I learned it from Titus, and I was about to raise my hand and tell you at the end of section 7, hey, have you heard of Leman? So
no
I'm
kidding.
jealous of you that you've got Titus now.
Yeah, you probably should be.
Yeah.
But yeah, okay, yeah, no, you're absolutely right. You said the declining quality was later. Like
20 years later.
20 years later,
and
yeah.
also in a time where like Windows 95 had shipped and Photoshop was on version N. And
right.
Like I think it became much clearer as we stopped just building toy programs for playing chess.
Yeah.
And building like internet programs and stuff that like these are so true in our modern world.
Yeah, great point. That's going in the that's going in the deck. Thank you. I got to add the dates. Okay, so what's the point of me showing you any of this? Partially because I think it's cool, and partially because I think these criteria can give us a bit more formality to the notion of stable software that I presented a little bit earlier. Stable doesn't mean that the code hasn't been touched since the 90s. I made that mistake when I first gave this talk. That's what I thought stable meant, but it's really not true. It has more to do with the specification. If the spec of your program hasn't changed in a while, now's a good time to try looking at it, consider it stable, and then generalizing it. So ask yourself, when was the last time my spec changed? Not my code. You're always going to try to make it faster. You're always going to update it for new operating systems, like the natural process of rot and mitigating that rot. But when was the last time you really changed the spec of your JPEG parser? The 90s, maybe? That would be a good candidate to consider for generalization. So ideally, I guess, I'm still new to these ideas, your code base would be comprised of these interconnected S and P programs, the simpler ones with very clear specifications, each with totally unambiguous specs, right? You leave the S programs alone. You don't need to update the 8 queens problem that much. And you would task expert optimizers with making your P programs a little bit faster. And then your user interface would just be an E program that's just thoughtfully guiding your users to the solutions that all of these S and P programs are producing. My point is, if you can try to pull subcomponents of your application or your code base into these S and P categories, you can systematically reduce the complexity growth of your programs and do a better job at like managing the stuff that needs to be updated because of the language evolving versus stuff that needs to be updated because requirements are changing. Knowing what you're doing can make your life a lot easier. All right, I'm low on time here. So I made it. Yeah, key takeaway 8 of 8. Identify stable specifications and generalize their implementations. Wow, that's all I got. Thank you everyone for listening. This was a lot of fun. I'll take questions. Yeah. Wow, that is very red. Yeah, I didn't realize that when I made the deck. All right, what's up? Yes, in the back.
So it's interesting that the whole like concepts things comes out of like Alex Stepanov's work with like algorithms and data structures, which are one of the most specified areas of computer science, right? Like sort, like there's not much ambiguity about what sort is supposed to do, right? Or like you know, or a vector or whatever, which is you know where the concepts like first kind of came out of. Like,
it's very interesting. I think also the spec sounds simple until you try to write it, until you try to write it formally and convince yourself that you're saying exactly what sort means. yeah, I don't know. That can be more difficult than you think. Yes?
Can you go back to the set of the 4 things you had?
Yes.
Actually, I think, Aaron, you observed the wrong thing about declining quality.
Okay.
Whoa.
What you observed was actually increasing complexity. And I think what he's saying there in declining quality is even if the program doesn't change, users will think it'll have the appearance of declining quality because the bar will be rising around it.
I think that is an interpretation. I like my feeling interpretation better. But you're right that most of my feelings come around complexity. So
right, like the increasing complexity is the thing that just happens naturally to code bases as people like poke and prod without like really effort to hold it down.
it's true, but that happens to S programs as well, right?
Yeah.
If you do poke and prod them, and you have to work on that. But there's something different about E programs, which is people poke and prod just because they want to, or because some product manager said to, right? Not because something changed about the spec or whatever. I don't know.
Is that true? Are people changing like the 8 Queens puzzle? Are you going to change that just because you're bored?
You are going to change. Well, like you said, it doesn't mean the code hasn't changed since the 90s, right? You're going to change it because there's some large-scale change that changes the semantics of some string view return parameter or something.
Yeah.
You're not going to change it because the problem changed. But it does. The code does change, you know.
Yeah.
And sometimes I have this other feeling about S programs, which is you talked about how they're candidates for generalization, and I agree. But I usually think about this in terms of refactoring is the process of pushing code down to more S programs. Like if you take a P program and you do a really good job refactoring it, you get more S programs out of it that can be reused elsewhere. And they don't even need to be generic, right?
Yeah, yeah.
So what I'm trying to say is that refactoring process often involves adding and deleting S programs or splitting them or combining them. And when I say, I hate these names, by the way. I wish you'd come up with better names. When I say S programs, I essentially mean small libraries, right?
Yeah,
like one function library.
Do one thing well, yeah.
Do one thing well.
Yeah.
Do one well-specified thing well, exactly. But anyway, so you do wind up changing them if you refactor. That's an example, I would say.
Yeah, I hear you. I don't have much to say to that, but I agree with everything you said.
If you call an ordered map an S program.
I do, yes.
I've made a lot of my career out of poking and reorganizing an S program.
Yeah.
Would you describe your task as optimizing the unordered map?
Yeah, although I've had to tweak the definitions here and there where the definition made it hostile to its own performant implementation.
I have to think about that. Thanks for sharing that.
This is what I mean too when I say refactoring. Changing the specification for an S program can also be valuable. And that often involves changing the code too.
Yes.
But you might want to tweak it. Like for example, if the concept originally said that the post increment or whatever had to return a reference, you change the specification, say void is fine because it turns out that was a good idea for some performance reason. Like you do wind up changing specs too, and it remains an S program.
I agree. Yeah, I agree. David.
I didn't expect to learn something from your talk, so thank you for...
What a strangely backhanded compliment, David.
Because I had seen it before, okay?
Okay, yeah, fair enough.
This stuff is really interesting. The question I have for you is, what portion of a software engineering team would you say should be doing the skill set where they're writing concepts in generic programming, and what percentage should be doing the not that stuff?
I have no idea because I haven't tested it. I don't know. We need to experiment and to try to answer that question well. Off the top of my head, I don't know, 5% of your team, 10% of your team, someone that's dedicated like full time to doing this work feels right. But again, in practice, it might be completely different. I have no idea. It also depends product to product, right?
Non-zero is a start, right?
I agree.
It's often zero, so anything that's non-zero is good.
I'll go with that.
And at least one whole person, I think.
Yeah.
Well, I mean, like not a person who does it every few weeks for one day. Like.
I understand. Yeah, whole person just made me giggle.
Yes, agreed.
Cool. Other questions? Preferably four-handed. Yeah. All right. Cool. Thank you all for your time. We're calling it. We're done. Talk to me afterwards. Thanks, y'all. Appreciate it.